I would like to start by first thanking every one of you for attending this event, this Undergraduate Research Expo 2020, which is featuring flash talks from 8 undergraduate students who completed research projects over the summer. This year's expo is different from the previous years, when the students usually were presenting their posters in the school atrium. But I hope that this virtual event will be as successful as in the previous face-to-face events that took place in the past. So I want to note first that in addition to the presentations that we will see today, all the students have also prepared posters which are available in the undergraduate student information page on Moodle, and I have posted the link for that in the chat. So please check out the posters as well on Moodle for more details about these projects. So the research internships that will be presented today were planned about this time last year, but due to the pandemic, students and supervisors had to work on an online setting for the first time. There were more challenges to overcome this year. However, we had 9 research internships were successfully completed, thanks to funding from the London Mathematical Society, the School of Mathematical Sciences, and other personal grants. So many congratulations to all of the internship students for their hard work and dedication. I hope that you have all enjoyed working on the mathematical project last summer, and that you have found doing these research projects to be a valuable experience. We look forward to listening to your short talks and learning about your achievements of these projects. So thank you also to the project supervisors as well for offering your time and working together with the students for on these projects over the summer. And I would also like to card reading academic process. And last but not least, thank you to Vanessa for her help in organizing this event. So some details about how this event is going to run. Each student will give a flash talk on their project. These talks will be very short, about 3 to 5 minutes long, and there will be time for questions after every talk. We will begin with talks on pure and applied mathematics, and then these will be followed by a short break, and then talks on statistics and mathematical physics from 3 p.m. onwards. So I will be changing the slides, so every student who will be presenting at any point, please let me know when you want to change slide, and I will do that for you. The next presentation will be given by Emily Cowley. Emily, are you here?
Yes, hello. Hi. If we could just go on to the next slide. Just the next slide now, thank you. So basically my presentation was creating interactive apps using RShiny, and these are apps which we aim to embed in notes or as additional resources for students to help them understand more. So topics that are typically found more challenging in lectures and in modules were going to be explored. You might ask yourself, why would you consider this? There's actually been a study by the PNAS on the left about somewhere in America, and they've analysed 225 different studies on scores in STEM subjects, and they actually found that students that had traditional learning, so it was a comparison of traditional lecturing versus active lecturing, where the active lecturing was more lectures in person and labs and more interactivity with the content and module. And they found that students that had active learning had improved exam scores of around 6%, as well as the other traditional learning students being 1.5 times more likely to fail. So that translates to students moving from about the 50th percentile, so about a 2.2, to the 68th percentile, so a 2.1. So there is proof that interactive learning does help improve students' exam scores and scores overall. So my project involved learning how to code in R Shiny, which was interesting as all of the variables, or a lot of the variables, are interactive variables. So it's quite difficult to, or reactive functions. So it's quite difficult to debug because like the functions change depending on user input. So you can have sliders and students can just simply select values on that, and then it changes all the code and plots different graphs depending on the values selected. So it was interesting learning to debug that. And I began in the first few weeks with very simple apps for that. And then as the weeks progressed over the next 8, I started improving them. I added a bit of CSS, so some images and some colors to make them more visually appealing to students if they were to use them. And if they were to be embedded using things like Learn, I think it was, into lecture notes to make it all of more of a succinct thing and give a visual representation of concepts that would happen. So if we, in total, I created 8 apps over the 8 weeks. So if we click onto the next slide, Anna. Yeah, so these are 4 of my apps. In the top left, we have a linear regression app that takes it takes a COVID-19 data set. I tried to be applicable to the times and the data now. And it's extracted the data from 5 different countries. So I think it's Italy, Afghanistan, Spain, Germany, and China, I think are the 5 I just chose. And then you can select, with just seeing the data, a gradient and an intercept for a line, which will then be plotted. And you can try and get as close just with that and with the sum of squares being calculated for you by the computer to minimizing the sum of squares and finding the ideal gradient line for your data. And once you've reached that, you can then reveal the correct line, which will be plotted as well on the graph. And then they'll tell you the coefficients, so you can see quite how close you've got for each of the data sets. And it goes through the process of, like, if you to make a linear model in real life, you have then after that, you look at the residuals for both the line you picked as well as the actual fitted line, and you can compare them and then look at the transformations on the next tab. So if you wanted to do like log transformations or square transformations to compare how they affect the data and the residuals to see how it looks then. And then on the final page, you use your, you use the fitted model in the end, just for simplicity, to predict, you can enter in and predict how many cases of COVID or how many deaths there would be in relation to how many cases based on the linear model that you selected or you created. And then there's another little selection to that where you can actually visualize what it would have been if a statistician had been given the same data, or a lecturer in this case, what they would have concluded from what they've given, and the same sort of app to see whether you're following the right sort of lines and if you understand it, and general hints for in future linear regression. By the way, all of the URLs are on the poster, so you can actually go and use them in your own time. I think it might be a bit difficult to go through it now, but if you feel like using any of the apps, they're on the Moodle site, which I'm sure Anna will send if the chat doesn't work. And then the one on the left, the confidence intervals. So you have, it calculates confidence intervals for both when theta is known and unknown. So it uses approximations for them and the S-squared values. And it then has a plot at the top, in the top left, which gives you the proportion of the confidence interval for each sample that you select, and then the proportion of them that are in that have the true value in its interval. So you can actually see how changing the value of alpha from like 0.01 and 0.05 changes how the proportion of confidence intervals that contain the true value. So it's a more visual way of seeing how confidence intervals work. And then the controlling FDR and FWER, false discovery rate and family-wise error rate. I didn't actually know these topics before doing the this project, I learnt them because I believe they're more in the module 4 that Chris was running. That is maths for scientists, something like that. And so I learnt these to create the app and do that. So I probably won't describe that. And the one on the bottom left is about tests. So for hypothesis testing, often it's difficult to just take from the words, from a description, what you're actually testing. So it works on just knowing what sort of test to implement, whether you implement a 2-sample Z test, a 1-sample Z test, a t-test, and all those sorts of things. And it cycles through a variation of different questions. And then there's also the flow chart, which I think is in the probability notes, at least my probability notes. And it uses that flow chart as a hint, so you can see what ones you can select. And then if we head on to the next slide, you can see the other 4 apps. Yeah, so in the top left, we have one that does correlation. So you can change the correlation between X and Y and see how it affects each of the respective things. I think it was, yeah. And so you can see how different things affect the correlation as well. And then we have the maximum likelihood estimators, so you can graph for both a binomial and for a Poisson, the ECDF and the likelihood function to see how with data these things change. And then the bottom left, we have power and error, an app on that, which you can look at the type 1 error and errors by overlaying your H0 and H1 graphs, and then seeing underneath the area of these which intersect and which corresponds to the error of type 1, error of type 2, and the acceptance and rejection region for H0. So you can change the values for what your, I think it was for the mu and theta for these, and then see how those affect each of the things for your hypothesis, which was H0 equal to 1,000 milliliters, yeah, and H1 less than or equal to 1,000 milliliters. And then for the app sample versus population, you compare, you can look at how with different sample sizes, as n increases, how it converges to your population of, so you select a population like a binomial of size NP, and then you take many samples of it and see how as the samples increase, it gets closer and closer to the original population. And it that's with 5 distributions, I think a chi-squared, binomial, Poisson, normal, and the other one I've forgotten now. And then the second tab is a sort of a game where you're given a distribution and you can overlay a random data distribution, and you can overlay different lines corresponding to the several distributions, and then it's up to you to decide which distribution do you think corresponds to this data set. So it's trying to emulate a bit more real life, and if you're a statistician and given a random set of data, what distribution would you use to predict your data set, and how would it work? But yes, and then if there's any questions, I'll be free to take them.
Thank you very much for the talk. Do we have any questions for Emily? Yes, Chris?
Yeah, hi there. Yeah, I just want to say thank you for all your hard work on this project. And yeah, I just wondered, did programming the apps help improve your understanding of statistics? And do you think other students could learn statistics by programming the apps?
I did actually feel like I understood what I was doing better, having to find out where it was going wrong, as well with it being an interesting way of trying to actually understand every line of the code to find out where the error was. And yeah, graphing it as well did help me visually understand it. It was much better for understanding. I thought I definitely came out better for it. But I don't know whether would you try and give every student a different topic to understand or to make an app of, or would it be for every student gets the same one?
Yeah, so yeah, it doesn't necessarily need to be for assessment, but just as a way of learning how a method works. You know, so sometimes when I'm trying to learn how to do something, it's only when I sit down and try to program it do I really think deeply about some of the aspects of it. So yeah, kind of learning by programming rather than
I think it definitely does help. I suppose then it depends on whether you can encourage students to do that, whether the students who will do that already do understand the topic better. But I don't know.
Yeah, thank you for your hard work on the project.
Thank you.
Yeah, it taught me a thing or two, and some of the students on my module will now be experiencing Shiny apps.
Thank you.
Are there any more questions? So if not, thank you, Emily, again.
Thank you.
We can now move on to the next talk.